So we're now ready to define the derivative as a function. In the last set of videos we introduced the derivative and gave the definition of derivative at a point, but it turns out that we can define the derivative as a function itself, right? And you'll see the definition here of now the derivative of the function looks very similar to the definition we gave before, except instead of a particular value of x, say a, where we had f prime of a, and the limit as h goes to 0 of f of a plus h minus f of a over h, we now are just replacing a with x, any real number that is in the domain of the original function. And now this new function called the derivative, right, of the original function f, its domain will be essentially all values of x where this limit here exists. Okay, if this limit exists, then the derivative exists. The derivative, we've already said, what does it do? It's a function now, and you input values of x, and the outputs are the slope of the function f at the point x comma f of x. That's how we can interpret the output to the functions. That's what they represent. Okay? So when we evaluate the derivative, what we're going to get is the slope, right? Again, the slope means the slope of the tangent line, as we showed in the last lecture, right? The process of finding a derivative is called differentiation. Differentiation. So this is the term we use. In fact, this calculus we are now doing is sometimes referred to as differential calculus. Now, a function is said to be differentiable at x if its derivative exists at x. In other words, provided this limit exists at x. And so you need to understand this definition and know it, because we will use this time and again. So when we say a function is differentiable, then that simply means that its derivative exists. Right? If it's differentiable at a point x, its derivative exists at x. Now, if a function, if we're looking at an interval, then a function is differentiable on an open interval if it's differentiable at every point in that interval. Okay. I'm not including endpoints here. If we include endpoints, we will talk about the derivative from the left and the derivative from the right, and similar to what we talked about with continuity. And we'll talk about that a little bit later. And we also will talk about the relationship between differentiability is the way we say it, and continuity. So is there a connection there? And we'll be looking at that in this lecture. Now, notations for the derivative. So this is the very common notation we introduced last time, and this is the f prime notation, right? This is read f prime of x. It's the derivative of the function f evaluated at x. Okay. Some other notations that we'll use are here. This is dy dx, dy over dx, or dy dx. And let's just jump down to that. This is the so-called Leibniz notation. Dy dx is read the derivative of y with respect to x. And this was used by Leibniz. We talked about Leibniz and Newton as being the founders, quote unquote, of calculus. And a lot of the notation that we use, though, actually comes from the way Leibniz did things as opposed to what Newton used. And so we sometimes refer to this as the Leibniz notation. Here's the idea of the Leibniz notation. When we talk about dy over dx, what are we talking about? We're talking about taking the limit as delta x goes to 0 of delta y over delta x. This is change in y over change of x. What is the slope, right? And the slope of the secant line, right, the change in y, would be f of x plus delta x. Of course, we're using delta x here in the notes we've been using. That was the letter h usually, right? F of x plus h minus f of x over h. So we're just using delta x here instead of h, which is what it is, right? The change in x, delta x, change in x. And so the limit is h goes to 0, f of x plus h minus f of x over h. That indeed is the derivative. So that's the idea. The dy dx, think of a slope, right? Change in y over change in x. But the dy and the dx are infinitesimally small changes. very tiny change in x. What's the corresponding change in y? So you can kind of think of this as a fraction, but really this is all one piece in terms of it represents the derivative. Okay. Some other notations. Well, let me jump over here. The d over dx and the big D with a subscript x, these are called differential operators. And what they say is, they say take the derivative with respect to x, and then in parentheses what function they're talking about. So here the derivative with respect to x of f of x would be also f prime of x. Both of these notations are valid notations. Same thing here. The derivative with respect to x of f of x is f prime of x. Okay. I don't use the capital D notation at all. You may see later on in your career, in Calc 2 or something, an instructor may use that notation, but that's what that means. Okay. Prime notation, right? F prime of x. If we just have y as a function of x, we might just do shorthand y prime. One thing we lose about the prime notation is what is the variable we are taking the derivative with respect to. We assume f prime of x, that since x is in parentheses, that's the independent variable, that's the variable we're taking the derivative with respect to. But when you write y prime, you kind of lose that information. It's usually not a problem. We usually are only dealing with one variable functions, but later on we do want to be able to differentiate when we have more than one variable going on. And so Leibniz notation is very helpful because it tells me the derivative of y with respect to x. Now notice that with this differential operator notation, this right here is the same as the derivative with respect to x of y. dy dx is the derivative with respect to x of y. So don't think of this as being a fraction, dy and dx, as being quantities in and of themselves, although we can sometimes think of it that way. Small change in x, what's the corresponding small change in y? What's the slope, right? Very close to the point of tangency. But this is the way we represent the derivative of the function. Okay, so dy dx is equal to the derivative with respect to x of y. Now, one thing about evaluating the derivative function, right? So when we have a function, we want to say input a value of x and get the output. The f prime notation works nice because I just do f prime and then put in parentheses, say I want to find the derivative at x equal 1. I'd say that's f prime of 1. If I want to find the derivative at x equal 2, f prime of 2, and so on. But here we don't have the parentheses or the input, and so what you'll often see is evaluation this way. Dy dx, and then a vertical bar. And if you remember, vertical bars in mathematics means evaluated at, or such that. And then as a subscript to that, then we will write the condition we're going to evaluate it, in this case at x equal a. So for us right now, this was the way we will denote evaluating the derivative of y with respect to x, right, dy dx, at x equal a. Okay. All right, so let's take a look at an example here. Let's find the derivative using the limit definition of the derivative as a function now. And so I'm going to let y, right, be a function f of t, right, which is the square root of t minus 2. And I just want to show you the different notations we can use then. We can say the derivative of y with respect to what? What's the independent variable? T, right? Input a value of t, we can find the corresponding output y. So t is the independent variable. So I can be finding the derivative of y, we say, with respect to t. Okay, that's one way I can write it. This is also take the derivative with respect to t of y. Both of these are the same notation. Okay. Don't do dy dt and then parentheses y, because then you're saying multiply the derivative times the function. That's not what we want. Okay. Or you can do y prime, or since I've called this f of t, f prime of t. Okay. So these are all different ways that we can write the derivative, and we'll interchange these. But you need to be familiar with all of these notations. Okay. But now I'm going to use the limit definition up here. Notice I've got x as my independent variable. Here it's t. So it's just changing the independent variable. And there we have. All right. So let's replace f of t plus h with what? F of t is t minus 2. So if I replace t plus h, or t with t plus h, I get up top the square root of t plus h minus 2. That's f of t plus h. What's f of t minus f of t? F of t is just square root of t minus 2 all over h. Now if I try and plug in directly to evaluate this, of course we know what's going to happen, right? I get 0 over 0, right? So again, this is 0 over 0, and so I'm indeterminate. I've got to do some work. How do I proceed here? Do you remember? This goes back to finding limits algebraically. Notice I've got radicals up top. I can rationalize by multiplying what? Numerator and denominator by the conjugate. The conjugate of this is the square root of t plus h minus 2 plus the square root of t minus 2. Of course, what I multiply the top by, I also have to multiply the bottom by. Okay. Now, across the top, we're going to FOIL this out. First times first, square root of t plus h minus 2 times the square root of t plus h minus 2 is just t plus h minus 2. The outer, right, is positive, this one times this one, and the inner is negative this one times this one. So positive, negative added together is 0. The inner and outer terms add to 0. And that's the whole point, remember, of multiplying by the conjugate. That will always happen. The last times last, negative times positive, is negative square root of t minus 2 times square root of t minus 2 is t minus 2. Be careful, make sure that's in parentheses so we can distribute that negative sign through. Now on the bottom I've got h times all this stuff. I'm going to leave that factored. So I need a parentheses around this part. So I'm not going to distribute the h through. But let's talk about, can we simplify this thing up top here? Yeah, just distribute that negative sign. I get t plus h minus 2 minus 2 plus, minus t plus 2. All right, make sure we see that. And then what's all that simplify down to up top? T minus t, negative 2 plus 2, I'm just left with h. So this is the limit as h goes to 0 of h, is what the top simplifies down to, over all this. T minus 2. And so now we notice, as usual, all right, when we're in this process, we're going to eventually find that common factor in the numerator, which is h in this case, and h divided by h is 1. And now what am I left with? 1 divided by this stuff. That is actually continuous at h equals 0. I can now plug in directly. H is 0, and what do I get? So minus 2 plus. Right. So that's going to be just the square root of t minus 2. So what do I have? The square root of t minus 2 plus the square root of t minus 2 is 2 times the square root of t minus 2. And there is our derivative function. So unlike what we were doing last time, where I was finding the derivative just at a point, right, for a particular value of t, right, so when I evaluate f of t, like if I was doing it at t equals 6, I would plug in and get square root of 6 minus 2, square root of 4, I'd get 2, right, input. So this would be 2 and then I would simplify it that way. But in this case, we do it just in terms of t. So now I can find the slope at any point. So what's the slope of this function? What's the slope of the tangent line, or the slope of the function, at the points 3, 1 and 6, 2? All right, when I plug 3 into the function, I get 1, and when I plug in 6, as we said, we get 2. What's the slope? Well, the slope is the derivative. So at 3, the slope would be f prime of 3. So input 3, what's our corresponding output according to this function? Replace t with 3. And 3 minus 2 is 1, square root of 1 is 1, I get 1/2. Okay? So this is the slope of the tangent line at the point 3, 1. F prime of 6 6 minus 2 is 4, square root of 4 is 2, 2 times 2 is 4, I get 1/4. And so there's the slope at the point 6, 2. Is the function differentiable? Oh my goodness, what's that mean? We just talked about it. Differentiable means what? The derivative exists. Is the function differentiable at the point 2, 0? Well, that's when t is 2. Well, the answer is no, it's not differentiable, because f prime of 2 is what? If I plug in t equal 2, what happens? Division by 0, right? F prime of 2 is 1 divided by 0. That's undefined, right? So the derivative does not exist. That limit is not going to exist as a finite number. As a finite number. Now, let's interpret this graphically. Let's see if we can interpret this graphically. Here's the graph of the function. This is the function y equals the square root of t minus 2. And 2 points of interest we said were what? The point 3, 1, input 3, output 1, and 6, 2. Okay. At 3, 1, what does our slope look like? Well, what did we say the slope was supposed to be? It better be 1/2, right, according to this. So if I go right there, I just want to estimate the tangent line at that point. So I'm just going to touch it locally, lower it down, so it just touches there. So there's my estimate. The bottom of this ruler is the estimate for the slope. Well, what about that line? Does it have a slope of about 1/2? Going from one point, where's another point? Right there is another point. I go up 1, over 1, 2. So we can see, right at that point, I'll thinly sketch that line. That line has a slope of 1/2, and that's consistent with what we said there. At 6, we said the slope was 1/4. If I try and find the tangent line at that point, just touching it right there. What is that line there? That's the tangent line about. What's the slope there? Going from this point that's on the line to our point, we go up 1 and over 1, 2, 3, 4. So 1 divided by 4, 1/4 is the slope. Let's do one more example. Let's find the derivative of this function. So let's go right into it. Notice I'm calling this function g and not f, so we're looking for g prime. This is the limit as h goes to 0, g of x plus h minus g of x all over h. Okay. So this is the limit as h goes to 0. What's g of x plus h here? Replace x with x plus h. I get 3 divided by x plus h plus 1. That's g of x plus h. What's g of x? That's just 3 divided by x plus 1. All over h. Of course, if I plug in directly, we know what's going to happen, right? When I let h be 0, this is going to be in the indeterminate form. Okay. How do we simplify and evaluate this limit algebraically. Do you remember? We're going to clear out these smaller fractions within the big fraction. The way I'm going to do it, you can combine these as one fraction and then divide by h, or multiply by 1 over h, or I'm going to multiply numerator and denominator by the least common denominator of all my smaller fractions. This denominator is x plus h plus 1, this is x plus 1, so it's just the product of those two. That is our least common denominator of all our small fractions, so I need to multiply both the numerator and denominator by that. Now here, when I distribute across the top, first of all, x plus h plus 1 down here will cancel with this x plus h plus 1, leaving the x plus 1 times the 3. And so up top, the first thing we're going to get is 3 times x plus 1. Then what? Distributing times this fraction, the x plus 1's cancel, and I have minus 3 times x plus h plus 1. Again, that clears out the fractions up top. Down below, I'm just going to multiply h times all this stuff. And again, I'm going to leave that factored. Since it's already factored, I want to leave it that way. Up top, I've got to do some work, right? I can distribute the 3 here and the negative 3. And what do I get up top? I get 3x plus 3, right? Distributing that 3 through, and then negative 3 times x, negative 3 times h, negative 3 times 1. And what does all of this up top in the numerator simplify down to? What do we do after we combine like terms? 3x minus 3x, 3 minus 3. We're just left with negative 3h up top. Okay. We're still indeterminate, but there's my factor of h that I'm looking for, right? H in the numerator, h in the denominator. So I can indeed, right, cancel that out that way. And so basically I have the limit as h goes to 0 up top. I just now have negative 3. Down below, this h is gone, and I have x plus 1. And now I can plug in h equals 0. And what happens when I plug in h equals 0? Because this is now continuous at 0 when h is 0. So I get negative 3 up top, x plus 1. And if h is 0, this is just x plus 1. What's x plus 1 times x plus 1? It's x plus 1 quantity squared. And there is our derivative. And there's our derivative. Now, just checking, another way to check the derivative, again, this is going to tell us about what? This function here outputs the slope of the graph of g, right, at any value of x. So I want to look at the graph of g versus the graph of g prime. Hope you notice that both of these functions have a vertical asymptote at x equal negative 1. Here is the graph of g in a solid line, and g prime is the dashed line. And you can see the vertical asymptote at x equal negative 1. But let's just see, at 2, right? Think about, here's the graph of the function g, the solid line. At that point, what's the slope of the tangent line? If I try and draw and sketch it, we can see that it is about negative what? Notice it's negative because as we move down from this point on the line, the top of the ruler is my line, to maybe that point 5 comma 0, I go down 1 over 1, 2, 3, negative 1/3. Notice that's consistent with our formula. If I plug in 2 here, I get 2 plus 1 is 3, 3 squared is 9, negative 3/9 simplifies down to negative 1/3. So that's a good thing. And you can see that the value of the derivative here, right? At 2, what's the value of our derivative function, which is the dash line? What is that? It's negative 1/3 about, right? And you can see as I move along the graph of my original function for values greater than 2, moving from left to right, what's happening to the slope of the tangent line as I move through that? that slope is always negative, but getting what? Less negative. Getting closer and closer to what? Getting closer and closer to 0, right? Getting closer and closer to a horizontal line. We never quite get there. And so we have a horizontal asymptote for our derivative. Notice the slope is approaching 0 as x goes to infinity. On the other hand, if I move from the point 2 as x gets closer and closer to -1, as I move to the left there with my line slopes, what's happening to my tangent line slopes? They are getting more and more negative. You know, the line's getting steeper, but this is more negative, right? And we're, in absolute value, we're getting larger, but we're getting more and more negative, and so what's happening is we're approaching what? Negative infinity. We have a vertical asymptote, right? So there's the slope of the original function given by the derivative. Notice over here, at any point, the slope of our tangent line is also going to be negative. Say if I pick a point at -4, and if I were to look at that slope, right, it's going to be negative, which is consistent with our derivative function. The value at -4 is indeed negative. And as we move from left to right, what's happening to the slope? It is getting more negative, right, as I move from left to right along this curve, more negative, and so the dashed line you see is getting more negative as x gets closer and closer to -1. Okay, so hopefully you understand. It's going to take some while, but we'll look at this in the next video, graphically relating the derivative function to its original function.